Thanks, Jürgen, for the introduction, and thanks to everyone for being here. It's really a pleasure to be here and to have the opportunity to present my work. So I'm going indeed to talk about the processes of adaptation to spatio-seasonal environmental changes, and I will just start with a bit of context on these environmental changes that are faced by wild populations across the world. As we all know, ongoing climate change is altering the patterns of environmental viability, and we observed major changes in seasonality. There is an overall increase in temperature, which causes earlier spring and longer, warmer summer seasons. And this can cause phenological mismatches when two species interact and one is tracking the seasonal advances faster than the other. This is problematic if one species is a critical resource for another to achieve seasonal biological activities that matter for fitness. For example, in many temperate passerine populations, a mismatch is observed between the food peak and the peak of parental care, as is the case between tits and the caterpillars they use to feed their chicks. And the same kind of mismatches is observed between the reproductive season of herbivores and the vegetation flush, as was shown in roe deers in France. And mismatches are also observed between the phenology of plants and their pollinators, etc. And all these cases are of major concern because they reduce reproduction and survival. And there's another major concern, which is the increase in frequency and intensity of extreme climatic events, ECEs, such as storms, droughts, or floods, etc., which are also characterized by seasonal distributions. And whether there is an overall increase in the variance or in the mean of weather variables, climatic conditions that were originally unlikely become more and more likely. And such extreme conditions can cause an exceptional stress to living organisms, going beyond the typical conditions to which their physiology was previously adapted. For example, these greater flamingos in the south of France, they are particularly sensitive to extreme cold spells in winter because when the marshes freeze, it prevents them from feeding and it makes them starve to death. And the wildfires that are increasing worldwide, they have obvious dramatic direct consequences on biodiversity, or these flying foxes here suffer mass mortality during heat waves when the temperature reaches 42 degrees in the shade in Australia. So by impacting survival and reproduction, all these perturbations, they will directly affect population growth and hence put populations at greater risk of extinction. But beyond these direct dramatic effects of changing circannual environmental viability, crucial questions are whether populations can actually overcome such changes and what will be the long-term consequences. And answering these questions requires to understand the dynamics of the phenotypic distributions of key traits that mediate the link between the seasonal environment and fitness, where some phenotypes can mitigate or avoid the negative impact of environmental perturbations. And I'm thinking here, for example, about phenotypes allowing individuals to match their phenology with beneficial seasonal conditions or to escape temporary detrimental conditions. So different phenotypes will differentially affect survival and reproduction, and this is natural selection, changing trait distributions within generations. And if there is underlying additive genetic variation, there may be an evolutionary response to selection, causing longer-term changes in trait distributions. And phenotypes may also directly change on relatively short terms due to phenotypic plasticity. And there may even be selection and evolution on plasticity. So we need to dissect the interplay of all these components if we are to understand and predict population responses. In fact, some very evident candidate key traits here are life history traits because they define the life cycle of organisms, they directly compose the fitness of individuals, and they drive spatio-temporal population dynamics. But I think that so far, studies have not really envisioned the life history traits themselves as the key responsive traits subject to ongoing adaptive evolution. And to fill this gap, we first need to conceptualize the quantitative genetic architecture of life history traits, which defines how the genotypes translates into phenotypes given development and influences of the environment. And usually for continuous phenotypes like size or mass or other morphological traits, we can simplify this into a linear model, just a simple straight line relationship. But for life history traits, most often this mapping is obviously nonlinear. And indeed, many key life history traits are fundamentally expressed as discrete phenotypic alternatives, like movement versus philopatry, dormancy versus germination, reproducing versus not, or clonality versus sexuality, etc. But their quantitative genetic architecture can be rationalized under a rather simple model, which is the threshold model. And here we assume that the trait is underlaid by a latent continuous variable termed the liability, and alternative phenotypes A or B are expressed when the liability is below versus above a certain threshold. And an individual has a given liability, which is a combination of genetic effects and permanent environmental effects lasting from developmental conditions. And for labile traits, the liability may also vary due to temporary effects of current environments, which can make the individual switch phenotype if it crosses the threshold. But the same effect won't result in a phenotypic change if the starting liability is too far from the threshold. And in this framework, if there is phenotypic selection, it is classically thought that it can only be directional. Indeed, either phenotype A has a higher fitness than phenotype B, or phenotype B has a higher fitness than phenotype A. So within phenotypes, there may be cryptic genetic variation, which is shielded from selection, but directional selection acting between phenotypes can still cause evolution of the liability either up or down. And accordingly, to have evolutionary maintenance of liabilities around this threshold, and hence of phenotypic variation, there must be some frequency-dependent selection whereby the most frequent phenotype is selected against. But I'm going to show that this view is probably a little bit too simplistic as things get more complex due to plasticity. And here you see that I've just flipped around the threshold model graph. So we can now add an explicit environmental axis and thus consider the plastic response of the trait. Here, for a given individual or genotype, the liability can change with the environment according to some reaction norm, which will result in phenotypic plasticity as the liability crosses the threshold. Yet, genotypes with the same slope but different elevations may show different levels of phenotypic plasticity. For example, here, the red and the orange genotypes, they show no phenotypic plasticity because they are simply too far from the threshold to cross it, and so they do not switch phenotype across the environmental gradient. And this remains valid if the liability reaction norms are not linear. Even in the absence of among genotype variation in liability plasticity, there may be emerging among genotype variation in phenotypic plasticity. In other words, strictly additive genetic and environmental variance in the liability result in genotype by environment interaction variance in phenotype. Now, if you imagine these genotypes as individuals exposed to an environmental gradient through time, you'll be able to observe the among individual variation in phenotypic plasticity, these different sequences, and hence possibly estimate the G, the E, and the G by E variances. And you may even observe that selection is actually not only strictly directional, but it can take a different shape For example, the pink individuals that switch phenotype, they may have higher fitness, indicating selection for phenotypic plasticity, and accordingly stabilizing selection on the underlying genetic variation in the liability elevation. And here, selection could also be directional or disruptive or subtle forms in between. So overall, we have an inherent interplay of phenotypic plasticity, genetic variation, and selection, which opens the door to complex eco-evolutionary responses of discrete traits. So we can apply these views to better understand what's happening in the wild, and it's what I've done for one key life history trait through which mobile animals can respond to spatial and temporal environmental variability, which is seasonal migration versus residence. And seasonal migration versus residence is the reversible movement between breeding and non-breeding locations across seasons, and it's one obvious trait that allows individuals escape harsh conditions occurring during the non-breeding season. And this trait can be variable within populations, which leads to partial migration when some individuals are resident throughout the winter while others are migrating. And accordingly, this trait is driving spatio-temporal population dynamics by distributing individuals in space across seasons and by spatially segregating different sets of individuals from the same sympatrically breeding population. It can make them experience different environmental changes, and so it implies high potential for fitness variation that may cause strong selection. And in fact, partial migration is very, very widespread among animal taxa. It's observed in many birds, but also in mammals, fish, and amphibians, and it covers a large breadth of life history diversity. And it also involves a diversity of movement patterns from the small-scale movements of red-spotted newts between a breeding pond and surrounding woods, or intercontinental movements of greater flamingo, and some species migrate south while others migrate to the north. Some do altitudinal movements, some do longitudinal movements, etc. So I study one of these partially migratory species, the European shag, which is subject to an intensive long-term monitoring program on the east coast of Scotland. And our study population breeds here on the Isle of May, where hundreds of individuals are marked with colorings every summer by colleagues from UKCEH. So thousands of individuals of known age and sex have been followed throughout their lives across multiple years, and their reproduction has been closely monitored, so we also know the details of their pedigree. And this system is of both particular value and concern because these shags experience extreme winter storms causing mass mortality. And what's happening under the strongest winds and rough seas is that shags, they can hardly fish because they don't see well in turbid waters, and the low temperatures, heavy rainfalls, and constant spraying from the sea hampers thermoregulation because their plumage is only partially waterproof. And so they end up dying very suddenly and in mass. But in winter, some birds remain resident on the Isle of May, while others migrate away, mainly to the north. And this may be a mean for the shags to escape the storms. So colleagues from the University of Aberdeen joined a team of field workers to go along the coast and recite individuals where they are, and hence phenotype them as residents or migrants. And the analysis that I will present today, they focus on the adults. So to give you an idea of the sample sizes, it's about 2,500 individuals or more connected through 7 generations in the pedigree, for which we had about 5,000 breeding attempts recorded and about 60,000 year-round resightings. And so it comes to the point where I need to thank all my collaborators with whom I've been embarked in this great adventure of studying seasonal migration in shags, notably Jane Reed, who's been my closest collaborator and mentor for almost 8 years now. also my colleagues from UKCH, and others at the University of Aberdeen and TNU, whose contribution has been pivotal in many ways. And without all of them, I clearly wouldn't be here to present anything today. So they really deserve huge thanks. And also today, I'm just presenting the work that I led on adult shags, but I wanted to quickly highlight that we have also been pushing this further in juveniles with my postdoc colleague Rita Fortuna and PhD student Cassandra Ugland. And we've also advanced the theory of partial seasonal migration with postdocs Anna Payo and Thomas Holland. So I invite you to also take a look at their papers. Okay, so now let's move on with the core methodology for analyzing the shag data. To make inference on phenotypic variation of migration versus residence using resightings, we need to handle the fact that individuals, they may often go undetected. And after the last observation, mortality is confounded with observation failure, which may depend on where they are, and so on their phenotype, which we are interested in. So accordingly, I developed a multi-state capture-recapture model that represents this full annual cycle of partial migration while accounting for the non-random missing phenotypic data and the associated uncertainty, which is due to spatio-temporal heterogeneity in resighting failure and mortality. And to represent this process of seasonal life history transition, I divided every year into 5 capture-recapture occasions. The first one is the breeding season, during which all the individuals are located on the Isle of May. And then individuals can either remain residents on the Isle or move to a migratory site where they will be in September. Then the September residents, they can either remain residents or move to a migratory site in October. And September migrants can either go back to the residency site or remain in a migratory site in October, and so on for November, December, and January, February. And then all the migrants go back on the Isle of May and residents remain there for the next breeding season. So I could use this framework to quantify natural selection acting on migration versus residence. And first, this model, of course, includes possible deaths at each time step, which allowed me to quantify survival differences between residents and migrants. So I obtained these estimates of seasonal survival probability for each consecutive occasion across multiple years, with residents in red and migrants in orange. And we can see already these major survival drops here and here that contrast with high survival in other occasions. And all these episodes, in fact, they concur with extreme winter storms that hit the east coast of Scotland. And in 2 cases, resident survival was much lower than migrant survival. In fact, migration provided shelter from the storm, resulting in very strong selection against residents, contrasting with typical neutrality or perhaps weak selection occurring otherwise. And if we then look at the resulting annual survival probability with red dots for the winter-run residents and orange dots for the winter-run migrants, well, we retrieve the very strong selection, which I think is a result that really stands out on its own because it's a rare result of major importance, as although it may seem obvious that extreme climatic events can cause strong selection, in fact, there is barely a handful of examples that exist in the literature. So this one is another critical one. And therefore, we were able to quantify this apparent directional selection on the phenotypic dichotomy of migration versus residence and showed that extreme climatic events strongly select for migration via survival. Then I extended the model to quantify breeding success differences between residents and migrants, and I focused on the last transition in the annual cycle between late winter and the breeding season. And I divided the breeding stage into every possible breeding outputs from 0 to 4 fledglings, and I modeled this fledgling productivity as migration dependent. So we got these estimates of breeding success against year, where we can see that residents in red here, they have consistently higher productivity than migrants across years. Except that this effect is absent or perhaps even reversed just after the extreme climatic events, which suggest a carryover effect of the extreme storms that will strengthen the selective impact that these storms had against residents through survival. So we also showed that benign conditions typically select for residents via reproduction. And now if we look at an estimate of annual fitness, combining survival and breeding success, which in this case is the expected contribution of an adult alive in a breeding season to the population of the next breeding season, we can see that selection caused by the extreme storms clearly reverts the typical selective advantage of the residents. So there is fluctuating selection on migration versus residents occurring via overall annual fitness. And again, I think these results are notable because very few studies have demonstrated changes in the direction of selection. And it's also an original finding that these fluctuations, they arise from the opposite action of different fitness components. We would have documented variation only in the strength of selection and not in its direction if we had focused only on one fitness component. And these results highlight that extreme climatic events are likely to be a key driver of the eco-evolutionary dynamics of migration versus residence. And the strong EC-induced selection might contribute to maintaining this genetic variation around the threshold underlying partial migration. And it might be a route for evolutionary rescue against the increase in frequency and intensity of extreme climatic events, which could be very relevant to many animal species. So a key next step then was to fully dissect the eco-evolutionary dynamics, was to quantify the plasticity and selection occurring on plasticity. So let's go back to the initial conceptualization, to our threshold model to envisage migratory plasticity. Under a basic scenario with individual variation in liability elevation, but similar plasticity of the liability in response to winter progression. Some individuals start far below the threshold, so they never cross the threshold and they remain residents throughout the winter. Others start above the threshold, so they never cross and they remain migrants. But others start a bit below, so at some point they cross and they switch from residence to migration. So these ones express phenotypic plasticity and hence show a mixed resident-migrant phenotype. So I could refine my capture-recapture models to quantify the tactic proportions in the population, and I found that each of these tactics was actually present in a large proportion in the population. There were about 40% of full residents, 30% of mixed resident migrants, and 30% of full migrants, with important between winter variation around this average pattern. And I also quantified the probability of tactic transition from one winter to the next. So that's a higher level of plasticity occurring between years and depending on the level of within-year plasticity, which defines the different tactics. And we found that the full residents and the full migrants, they had very high probability to repeat their tactic. And when they switched, they preferentially switched to the mixed tactic and very rarely to the opposite full tactic. Meanwhile, the mixed resident migrants, they were less repeatable and they switched equally to full residence or full migration. So there is clearly structured directional switching, which is again rationalized under this threshold model. Mixed phenotypes are likely to switch in both directions between winters because they are individuals with liabilities close to the threshold. They are the most plastic overall. And full phenotypes, they switch directionally to the middle of the spectrum because these are individuals with liabilities far from the threshold and they are the least plastic overall. And there is also high repeatability in the migratory tactics, indicating strong individual canalization, which reveals large heterogeneity that certainly exists in the underlying liabilities, part of which may be genetic, part of which may be due to permanent environmental effects. So there is substrate here for selection to act on and shape complex migratory dynamics. And accordingly, I used my model to quantify survival selection acting on these tactics and hence on migratory plasticity. And here we have 6 non-extreme years grouped together versus 3 years with extreme storms. First, in females, we see no clear survival differences in mild years. But in 2 extreme years, there was strong directional selection from full residence to full migration. And in another year here, there was strong disruptive selection whereby plastic migrants had the lowest survival. Now in males, in the mild years, there was disruptive selection of small magnitude. There was strong directional selection in the first extreme year, no evidence in the second one, and strong selection against full residence in the third year, or perhaps even stabilizing selection. So again, I think that these are really important results as we show major shifts in the magnitude and the shape across years and across sexes. And we also retrieve all the possible shapes of selection that I mentioned earlier can indeed act on the threshold traits. And these fluctuations of selections, they are responsible for complex dynamics within short time frames in interaction with the substantial rates of switching between the migratory tactics. And they also provide a mechanism by which genetic variation in liability and hence phenotypic variation may be maintained. And beyond these advances on the threshold traits and on migration, we are here measuring selection on plasticity, which is another thing that has rarely been done, and even more rarely in the wild. And even less studies have found actual evidence for a cost of plasticity, but I think we do here because in most occasions, the plastic tactic, the mixed resident migrants, they had lower fitness than inflexible phenotypes and even the lowest fitness in some cases in both benign and stressful conditions. So the critical next point then to fully understand the consequences of such selection was to conduct a quantitative genetic decomposition. So that's what I did, and I developed models to create the capacity for doing this. Specifically, I combined my capture-recapture model, allowing for full annual cycle inference on phenotypic expression of migration versus residence using reciting data, with a quantitative genetic threshold model using pedigree data, hence forming what we call it a joint multi-state capture-recapture animal model, which enabled me to decompose the trait variants into genetic and environmental components. And we did find some additive genetic variants indicating potential for microevolution of migration in response to selection. And we also found these very large permanent individual variants, mostly representing environmental effects lasting from plastic development during early life and explaining this canalization of migratory tactics. And there was also a fair amount of temporary environmental variants representing plastic responses to current conditions. But what does this actually mean in terms of the phenotypes that we can observe, migration versus residence, and hence the actual biological processes that they mediate? To find this out, I devised the mathematical solutions to achieve the back transformations of the variances from the underlying liability scale to the phenotypic scale of the trait variance. And we retrieved a modest additive genetic variance, quite large permanent individual variance, and notable temporary variance. But now we have a new and substantial fraction due to this emerging among individual variants in phenotypic plasticity that I mentioned earlier. And more precisely, we get E by E arising from interactions of environmental effects due to developmental and lay-by plasticity. That is, more precisely, early life conditions generate variation in the elevation of these liability reaction norms for the response to current conditions of the environment. And I think it's a very important point, which is too often overlooked, maybe more in this sort of quantitative genetic analysis, that in long-lived species, conditions experienced in the recent past may have major importance in shaping the response to present perturbations. And we also get the G by E that I mentioned in introduction, which quantifies how much the genetic variance in liability gets revealed through phenotypic plasticity and is hence exposed to these complex shapes of selection that we documented, the disruptive, directional, and also stabilizing selection, and thus may effectively fuel microevolution of migration and migratory tactics. But ultimately, for migration to translate into effective evolutionary resilience against changing seasonality and the increase of these extreme climatic events, there would need to be a causal link to genetic variance in survival. But the first question we need to ask before anything is whether there is any genetic variation existing in survival and how it is shaped across extreme events versus benign conditions. And survival, like migration, like many life history events, or actually all life history events, is fundamentally expressed as a dichotomous phenotype. Either you're alive or you're dead. And its quantitative genetic architecture is appropriately rationalized under this threshold model again. And again, we can conduct variance decomposition using a joint capture-recapture animal model, combining reciting and pedigree data to quantify the underlying additive genetic variance in survival, representing adaptive potential. And in principle, in fact, such analyses are even simpler than for migration versus residence because we don't have this layer of movements anymore. But it's also much more data hungry because individuals switch to death only once in a lifetime. And hence, it generates some issues with the amount of information that you have throughout the pedigree on the transition in this trait. So I did this, and I did it using even more data because now I could use the years prior to when the winter monitoring started. And we found non-negligible additive genetic variance in survival across 25 years, yielding a heritability of 4%, which is quite modest, but does demonstrate existing adaptive potential through survival. And so through which selection on migration versus residence occurring during winter storms could effectively act to enhance mean fitness in the population and hence contribute to evolutionary resilience of the population in the face of future extreme events. But remind that these extreme events, they also cause mass mortality. And consequently, we estimate this massive variation in mean survival across years. Typically, in good years, adult survival is very high. It's around 0.95. But there's occurrences of bad years when notable storms occurred and survival dropped below 0.85. And there are very bad years with the most extreme storms when survival is below 0.5 and can go down to as low as 0.18. So these extreme events, they disrupt organisms so much that they substantively impact survival, right? So they could likely also affect the amount of available genetic variation for survival, simply because different modes of vital functioning are probably coming into play in these good versus bad and very bad conditions. So I estimated additive genetic variance in survival, then separately in the good, the bad, and the very bad years. And we do find much higher VA in the good years, now yielding a heritability of 12%, which is pretty high for survival. And overall, this demonstrates, I think, that extreme storms constrain the capacity for adaptive evolution in shags. In these bad and very bad years, you see that the mode of the posterior distribution is on zero. So basically, we find what we would expect under a null expectation. So clearly, there is an important G by E here. And it is not such a good news because it might limit the effectiveness of selection on migration, which occurs during the bad and the very bad years. But we'll need to figure this out by further estimating additive genetic variance in survival and covariance with migration on the fine within season temporal scale of these extreme climatic events that can be at the scale of just a few days or a couple of weeks. And another key part of the story may be uncovered through similar analysis with breeding success. But still, I think these results, they really stress that robust prediction of evolutionary resilience to climate change, they really need to account for how severe environmental perturbation may impact and reshape adaptive potential. And now to end this talk, I would like to highlight some key prospects for the study of phenology that arose from our understanding of seasonal migration under the stressful trait framework. And again, key life history traits, they have these discrete or nearly discrete phenotypic distribution quite often. That's the case definitely for life history events. And many, if not all of these traits can be labile and play a fundamental role in how individuals and population adjust to seasonal environmental variation, perturbations, and changes. And as for migration versus residence, major aims in evolutionary ecology and demography are to understand and predict how organisms schedule the switches between these phenotypic states, which can happen throughout a lifespan, and that is a full life history, or within years, and that is phenology. For instance, we can define a general phenological threshold model, or PTM, which I will present here using the example of breeding time. Each individual would thus have a liability for breeding that changes through time given how environmental conditions progress throughout the breeding season. And so this viability will change until it crosses the threshold, leading to the switch from non-breeding to breeding, and hence the initiation of reproduction by the focal individual. And some individuals might reach this threshold later, and some individuals might even not reach the threshold and skip breeding in the focal season, as observed in many, many animal species. And importantly here, we get away from defining the trait as the calendar date by appropriately representing the biological mechanics that generate the date. We do get a distribution of breeding dates, but that is a byproduct of the liability dynamics and when individuals cross the threshold. And so this distribution of breeding dates can take any shape, depending on individual and seasonal variation in liabilities. It's not necessarily a Gaussian, and in fact, it can often be skewed, as is the case in this illustration, even though there are no differences in the elevation and in the plasticity of all these individuals. It's just the nonlinearity of the reaction norm that generates this skew in the breeding dates. So these are ideas that my student, Victorine George, is now implementing in her PhD, which includes applications on kittiwakes in co-supervision with Emmanuel Kam and Jane Reed. And we have now developed and tested an operational statistical framework that allows analyzing phenological data from the field to quantify the mean elevation and slope of norms of reaction to any environmental covariate driving phenology. And it's also operational for the estimation of individual variance in these reaction norm parameters. So Victorine has applied this model to illustrate its primary capabilities using a 32-year dataset on nest completion time in kittiwakes. And she formulated the liability for breeding or for initiating breeding as a function of day length and the daily change in day length, both representing key predictable axes of seasonality that birds are very well known to directly cue on, plus temperature anomalies representing stochastic fluctuations in the current environment, plus a random year effect for environmental fluctuations that are not varying within the season. And she found clear evidence for an effect everywhere, demonstrating and quantifying the well-known processes of photoinduction and photoinhibition of breeding physiology, but also sensitivity to current weather conditions, or in fact probably to covariant environmental factors like food resources as they fluctuate throughout the season. And also a large annual variation independent of the within-season variability. And importantly, she also found notable among individual variances in all the slopes, which demonstrates a substrate for selection to act on and possibly cause microevolution of the underlying mechanisms in the plasticity for phenology. So from here, the next steps would be to couple the phenological threshold model with an animal model to estimate the additive genetic components of these variances in the liability reaction norms, and also quantify how selection on the breeding dates translates into selection on these underlying liability parameters, and ultimately use this framework for predicting phenological adaptation to climate change. And now I just wanted to finish by showing these two graphs illustrating how the models predict breeding dates in the population. What the liability generates is a daily rate of crossing the threshold. So here, a probability of switching from the non-breeding to the breeding state every day. And from this, we can derive the distribution of breeding dates in the population, because it's just the compilation of how many individuals have switched on each given day, right? And you see that the years with late reproduction in blue and early reproduction in red, they mainly differ given the steepness and the top value of this probability curve. But there's further between year variation due to some secondary peaks here and there, and also varying speed of decrease, and also other small tweaks that are resulting from the stochastic weather effects through the season, here the temperature anomalies. And that is yielding distribution of breeding dates that are not only shifting to the right or to the left from one year to the next, but can also differ by the wideness and the height of the density peak, and also other subtle alterations, including skewness. Ultimately, this will non-linearly shape how selection that is directly operating through the breeding time will act on the underlying genetic variation in liability reaction norms. And I think this is probably where we can find some pivotal explanation why most phenological studies, they are generating evolutionary prediction that are often still failing to match the actual observations, because they define the traits and genetic variation directly as breeding dates, and they ignore the threshold mechanism that are underlying life history events. So there is certainly a lot of new and useful understanding and predictive capacity to gain from the phenological threshold model. And yeah, it's on this enthusiastic note of an application of this framework that I will close my talk, and thank you all for your attention.